So this time we will talk about something called Moon Moser inequality. So far, we have discussed about Turan problem. In Turan problem, if we have a graph with number of edges at least certain threshold, we want to show that it contains a copy of specific graph. So if the number of edges in G is bigger than extremal number of some graph F, then we have a subgraph in G. So we specify this number. That's what we have been doing. Then natural question is that, okay, we see that we can find a copy of F in G, but how many we can find? How many copies can we find? So we have already talked about this before in the name of supersaturation. But there, the bound we get was not so accurate. So what we have seen is that if this is well over this, then you can find many copies of this in terms of the correct number. So, so the statement is for given epsilon, there is delta such that the blah blah. So if the number of edges is well above, then the number of copies we can get is like delta times n to the copy of the number of vertices of F, n to the number of vertices of F. But this delta is, obviously not optimal. But for certain graphs, say clicks, we can get a much better bound. And one of them is this Moon Moser inequality. I said that for a given graph P, and let's say Ni with the number of copies of the complete graph on I vertices in G. And in particular, N1 is the number of vertices and N2 is the number of edges. Then what this Moon Moser inequality says that we can bound the number of triangles in terms of the number of edges and number of vertices. And it provides a number of triangles as a roll bound on the number of triangles. And there is also generalization of this, saying that not only about triangles, you can consider the similar problems for larger click. Then you get its lower bound. Indeed, these two bounds, lower bounds are there, but they are not tight. So for example, technically this bound can be tight if the number of edges is, specific number. So if the number of edges is exactly same as the complete bipartite graph, or balanced complete tripartite graph, or balanced complete R-partite graph, then this bound is exactly tight, but otherwise it is not. And Erdish and Rademacher have to find the type bounds on this. Type bound on this, the minimum number of NF in terms of say N2, which is the number of edges, and N1. Razborov use something called flag algebra to find the type bound for N3. Oh yeah, maybe I should also mention that if we know N1 and N2, you get the lower bound on N3. And then now you know N2 and N3, then you get lower bound on N4. And you get lower bound on N3 and N4, then you get lower bound on N5. So this, repeatedly applying this, you actually get the lower bound on arbitrary click, but that's also not tight. And Neris Radmar asked bound for this NS in terms of this N1 and N2. And Ryer find the asymptotically tight bound for N3, and Ryer find again asymptotically tight lower bound for general click. And for N3, later, Liu, Hayden, Picorco find an exact answer for the case that the number of edges not too close to click. Okay, so actually this Moon and Moser theorem we have discussed in the introduction to graph theory. And this time we want to prove a more general theorem. Okay, I will not repeat the... Okay, maybe let's prove this to, to get some idea. So how do we prove this Moon Moser theorem? So for each H E, we write G of E with the number of a triangle containing this E. Then what can we do? We can double count the triangle. Each triangle, for each E, for each H, we can count the, so what does it count? This is, if you add this up, so you consider all edges, and then you add it, then each triangle is counted 3 times. So when we count E, this is counted, and then when we count this is counted. When we consider this edge, this is counted. So we have this equality. And what's this? This is at least the degree of x plus degree of y minus n. So you want to count the number of vertices in the common neighborhood of x and y. And for that, there are n vertices outside. So you can, counting this way. So this is the lower bound on the common neighborhood, then what do we get? This is, you consider in terms of the vertex. And then for each vertex, you have degree x many edges. And for each edge, this x is added. This x is added. So how many times this degree of x is added? Degree of x many times. So you have this, and then the later part is minus n times number of edges. And you use the Cauchy-Schwarz here, then what? You get this. That's Cauchy-Schwarz. You apply the convexity of this square, then you get this. Then if you rewrite this, then what you get? This summation of degrees twice times the edges, number of edges, so you actually get what you want. So that's the proof. And you can even generalize this for larger clip. And there is even more generalization of this into hypergraph. So instead of graph, let's consider an R uniform hypergraph. Let's say Ni be the number of copies of I click, but the R uniform I click in the R graph H. Then what we can prove is that the number of S plus 1 click can be bounded from below by this expression. So this is a generalization of the Moon Moser theorem for hypergraph. So we will prove this. So again, just like before, what we did, we have a triangle and we count them in terms of edges. So now what? We want to count this S plus 1 click in terms of one smaller size click. So what do we get? We consider, say, if K is the vertex subset of a copy of S click, and let's say dk is the number of copies of S plus 1 click containing K. So we write it this way, meaning that if say S plus S minus 1, if say S plus 1 is R, then this simply counts the edges R time, and then this K could be any R minus 1 vertex subset. And then this counts the number of edges containing that R minus 1 vertex. So for higher value, if S is at least R, then we have an additional restriction that we only consider K, which induces a copy or click, click, yeah. And say for each that's K. We write K1 to KS with the S minus 1 subset. Okay, so you have KS vertices. So here you have S choices of deleting one vertex. Once you delete one vertex, then you get this vertex subset of size S minus 1. Then what we can show is the following. Just like we have proved the lower bound on the number of triangles containing an edge, we want to prove a number of S plus 1 clique containing this K, and that's like this. Again, you consider all possible subset of size 1 less. Then you add the degree, and then you subtract suitably and divide something. So, but you know that we consider the number of copies of clique on S vertices, which contains S minus 1 vertices. Okay, and one other vertex outside. Then that is what? You consider all subset, and then you add that their degree, and then minus 1. Why? You have this K, and what? This K is a copy of clique for Ki. You consider all the number of, cliques containing this, and that counts K as well, and then some other one. So this one, and this one, this one. You exclude this K. We don't want to double count and overcount this. So you count all other things. And this is what? Simply, you can write it this way. Okay. Now, what? What we want to count? We want to count this. So if you have K, then there is this vertex U. If this one is not a clique, so this is clique, then that means there is a non-edge here. So this is what? R minus 1 vertex. So if this U together with K does not form a clique copy of S plus 1 vertex clique, then U together with Ki this forms a copy of one less clique for at most R minus 1 choices of I. Right? So what's Ki? Ki is that here you delete one vertex. But if you delete one vertex as this, then this one together with U is not a clique because this non-edge is still there. So once you delete one vertex to obtain Ki, you have to delete one of these R minus 1 vertices to have some possibility of getting a clique. Otherwise, if you delete something else here, it's never a click. So there are at most r minus 1 choices of I. So from here, what? Yeah, maybe let's also mention this. So if U with K forms a copy of click, then this together with Ki forms a copy of one smaller click for S choices of I. So that's pretty much, I mean, easy for all choices. Then what do you get? You can bound this, say, by what? For every copy of S minus 1 click together with F, K and 1 other vertex, there are S choices of this copy of K sub S to the bracket R. And for all other cases, you have this S vertices, which is K, and out of N, you have this common neighborhood of all of this. So these give you click. And then rest of the choices, what you get? N minus S minus T of K choices of U. If you choose this, then this does not form a click, so there must be a non-edge F. Before, all of them gives at most R minus 1 choices of this being click. And then this being click is exactly what we counted here. So we have this, and that's what we want. How? So you have this, and you have this. So if you just spread it out, and then collect the all terms of D of K, and then you put it on one side, and then you move everything else, and you get this inequality. So now we have this inequality. We can, in fact, prove what we want. So how do you do it? Let's consider this expression. Okay, then what we have? So this is what we observed here. So this is same as f minus r plus 1 times summation of all degree of this k, where k was the overall clicks on S vertices. And what is this? This is for overall k over k, we apply this. Then this term and this term cancels out. And the remaining thing is for all I, you consider this. So for given k, there are S choices of kicking out one vertex, and then that's this. And you apply this as n minus S times R minus 1 minus S. And what does this become? This counts k, comma, ki. Yeah. So from the perspective of ki, what does this count? So whenever you have k, and one of the term is this ki, So that's same as you take a Ki, you consider, okay, sorry, let me correct it. For this K, you choose Ki and then you count all the clicks that contains it. So what is this? So this is U0, say U1, U2, U3. Then this is Ki. For each Ki, you count U0, U1. I mean, these two could be same. So it's like you fix this click and then you choose two not necessarily distinct vertices, which forms a click together with this. So that's what dki counts. So this is simply dki square, where this ki, let's write this way, k prime, because k is not there. K prime is a copy of f-1 click. So it's same as choosing s-1 vertices, and then the pair of two vertices counting together with this. And this corresponds to k, and then this corresponds to the clicks that's counted by this term. And here what? It's you count over all copies of s click, and you multiply n minus s times r minus 1 minus plus s. So this is what you get. Again, we use complexity. So this sum is overall choice of f minus 1 click. So this can be bounded by the square of the average instead of average over square. You get this. And then if you just compute it, then you get this bound. And what? You just divide this right-hand side by this number. And then you spread it out and you get exactly as this theorem is asserting. So once you have this, now what? You have this lower bound on the counting the number of clicks in hypergraph. And this naturally gives us super saturation results for click. And moreover, one corollary of this is that if you now know the number of edges, then you plug that in here with the number of edges and the number of vertices and number of edges, and this is number of triangle, as in the graph case. Let's say you have a R is 3, then what? And 4, you can prove a lower bound in terms of n3 times n3 over n2 minus and this provides what? So n2 here is just n choose 2, because so one vertex in graph, what's the click? Click is that the set of vertices, so that whose R subsets for all subsets of size R there forms an edge. But if your number of edges is R minus 1 or less, then it's vacuously a clique. So every subset of this with size I plus 1, which is none. So no edges, there are no subsets of this with the size R plus R, size exactly R, right? So none of them exist. So it's vacuously, they all forms H. So this is a clique. So this is N-choose 2. And then here you put the number of your hyperedges, then you get the lower bound. And once you get bound, then you repeat. Instead of this, then you write N5 in terms of N4 and N4 and 3. And you keep do that, then you get the bounds that the number of edges is at least this, then you must have a copy of KS in your hypergraph. And that yields the following bound on hypergraph Turan number. Okay, maybe we break the video here, that I will discuss about the hypergraph Turan in the next video. So anyway, we proved this lower bound on the number of cliques in hypergraph, and which is in general not tight, as I mentioned. But this provides a good lower bound, and that provides the hypergraph Turan number bound, upper bound, as here. So I will discuss about this in next video. Thank you for listening. I will see you in next video.